In this video, we will be having a quick revision of the chapter Work, Energy and Power. Starting with work. Work is said to be done when a force produces displacement. Work done by all forces, spring force, mg, pseudo force, frictional force, normal force and tension. Work is given by Fd cos theta. The SI unit is Joule. Work done for constant force and variable force. Area under force and displacement graph gives work done. Work done equal to area under ABCD. And if work is done by a variable force, then work is equal to integral F dot dr. Work done by conservative and non-conservative forces. Conservative force. Spring, gravitational and electrostatic forces are conservative forces. Work for these forces is stored in a form of potential energy. They are path independent. And non-conservative forces, are path dependent. And the friction is an example of non-conservative forces. Work can be positive, negative or zero. Positive work. If force and displacement both are positive or negative and theta is acute. If either of force or displacement is negative and theta is between 90 degree to 180 degree. Zero work. If work is equal to zero, force is perpendicular or to the displacement. Either force or displacement is zero. Negative work. If both force and displacements are positive or negative and theta is between 90 degree to 180 degree. If either force or displacement is positive and theta is acute. Power. The time rate at which work is done. It is a scalar quantity. SI unit is watt. Formula. dW equal to F dot dr and power is equal to dW by dt for small amount of work. Average power. Total work done in time t is average power. It is equal to work by time. Instantaneous power. Scalar product of force and instantaneous velocity is instantaneous power. P instantaneous is equal to F dot ds by dt, which is equal to F dot v. Special units. 1 horsepower equal to 746 watt and 1 kilowatt hour equal to 3.6 into 10 raised to 6 joule. Energy. Capacity to do work is defined as energy. It is a scalar quantity. Its SI unit is joule. Various forms. Heat energy, chemical energy, electrical energy, nuclear energy, mass energy equivalence. Work energy theorem. Net work done on an object by all forces will change in kinetic energy of an object. Net work is equal to change in kinetic energy. Work by conservative forces and work by non-conservative forces and work by external force is equal to change in kinetic energy. Types of energy. Mechanical energy. Sum of kinetic energy and potential energy. Kinetic energy by virtue of velocity is equal to half mv square. Potential energy by virtue of position, height, stresses within its and electrostatic factors. Gravitational potential energy equal to mgh. Elastic potential energy half kx square. Electrostatic potential energy k into q1 q2 by r. Mechanical energy is conserved. Energy in spring mass system. Total mechanical energy at each point is constant. Delta k plus delta v equal to 0. Maximum velocity equal to xm into root of k by m. Motion in vertical circle. In absence of dissipative forces, mechanical energy is conserved. Velocity is equal to root of 5 gl at bottom to reach the top. Velocity equal to root 3 gl at the bottom to cross quarter circle. Velocity equal to root gl to reach the quarter circle. Tension at any point on circle. T is equal to m into mu square by r minus mg into 2 minus 3 cos theta. Velocity at any point on circle. V square equal to mu square minus 2 gl into 1 minus cos theta. Collisions. An instance of one moving body striking with another. Collision of car with truck. Collision of ball in snooker are examples. Conservation of momentum. If net external force on system is 0, then linear momentum of the system is conserved. Delta p equal to 0. Initial momentum equal to final momentum. Nature of collisions. Value of coefficient of restitution defines nature of collisions. It is equal to velocity of separation divided by velocity of approach. Equal to 0, equal to 1, equal is between 0 and 1. Defines nature of the collisions. In elastic collision, momentum and kinetic energy of the system are conserved. E equal to 1, bodies do not stick together after collision. In elastic collision, momentum is conserved and E is between 0 and 1. Bodies do not stick together after collision. In perfectly inelastic collision, momentum is conserved. E equal to 0, bodies sticks together after collision. 1D collision. Delta P of the system equal to 0. E equal to V2 minus V1 divided by mu1 minus mu2. V1 equal to m1 minus em2 divided by m1 plus m2 into mu1 plus 1 plus E into m2 divided by m1 plus m2 into mu2. Velocity of first particle after collision. V2 equal to m1 minus 1 plus E divided by m1 plus m2 into mu1 plus m2 minus em divided by m1 plus m2 into mu2. Velocity of second particle after collision. Change in kinetic energy delta K, which is equal to half into m1 m2 by m1 plus m2 into mu1 minus mu2 square into 1 minus E. 2D collision. Bodies moving in a plane result in the arbitrary collision in different directions is 2D. Delta P equal to 0, delta Px equal to 0. m1 mu1 x plus m2 mu2 x equal to m1 v1 x plus m2 v2 x. Delta Py equal to 0. m1 mu1 y plus m2 mu2 equal to m1 v1 y plus m2 v2 y. Special cases. Hn equal to e raised to 2n ho, where e is the coefficient of restitution and n is the nth collision, ho is the initial height, hn is the height after nth collision. Vn is equal to en vo, n is the nth collision, v0 is the initial velocity and Vn is the velocity after nth collision. H is equal to h0 into 1 plus e square by 1 minus e square. H is the total distance travelled before it stops. T is equal to 1 plus e square divided by 1 minus e square into root 2h by g. T is the time taken by this ball to stop bounding.